Okay, this is section 5.1, linear algebra interlude, which I told you was coming. Up until maybe a couple hundred years ago, mathematicians were pretty much interested in just solving problems. They wanted to solve problems of motion, such as Newton, and they wanted to solve problems of probability, such as Pascal and others. You only had a few that were kind of interested in proving things in such a tight way that you could almost write a book with every line coming from a previous line. Euclid was the main example of someone who did that with geometry. He took things that had been used for centuries, probably millennia before him, and asked the question, how do we know it's true? And he came up with geometry, and he realized you only had to have 5 axioms, and from those you could get all the others. So he was kind of the exception. Other than that, people just kind of wanted to do stuff that worked. But then, within the last couple hundred years, mathematicians started asking the question, kind of how do we know that all of math works? And along with that question, we started kind of looking at mathematics and seeing how it could be generalized. For example, the integers are numbers such as what? -3, -2, -1, 0, 1, 2, 3, and so on. And people looked at those and said, "Oh, what are the properties that integers have?" And they say, "Oh, the important properties of integers is that you can add 2 of them, and there's an identity, and you can that sort of thing." And so developed the whole idea of groups from those. Oh, another one is that if you add them in different orders, then you can associate them differently. And there's this particular one that when you add 0 to anything, you get that one back again. And once you have this 0, if you have anything, then you can add a -a to that, and you get 0. And those were kind of, and then the last one is that if you take any 2 of them and add them together, you're going to get another one, right? If you take 2 integers and add them together, you're going to get another integer. Z is often used for integer. So those 4 properties are all brought together, and any collection of things that satisfies those 4 properties is called a group. And that's the whole area of mathematics done at upper level math courses at the college level. And kind of similar to that, something that you've probably seen in high school or someplace is you've heard the word vectors. And when you've heard the word vectors, you think of them as being these arrows that maybe look like that. And these arrows have certain properties. First of all, you can take these 2 arrows and you can add them together. Do you remember that? You put them head to tail, and when you put them head to tail, you get yourself another vector. And you can take any vector and multiply it by a scalar. If you multiply this one by 3, it's going to be 3 times as long. If you multiply it by -1, it's going to be in the opposite direction. If you multiply it by 1/2, it's going to be half the length. So you can multiply it by scalars. And these things satisfied certain properties too. In fact, there were 10 different properties that when people looked at these vectors that you've already maybe seen before, they saw that there were 10 properties that were kind of really that needed to be met in order for those vectors to be useful and in order to do things with them. So in that same couple hundred years, mathematicians just kind of decided, okay, instead of letting a vector just be this arrow, let's call a vector anything that satisfies those 10 properties. And so any collection of things that satisfies 10 particular properties that are all motivated by these arrows is called a vector space. And so I've got them already written down because it takes a minute or so to... Oh, I just touched the wrong button. I've got them written down because it takes a minute or so to write them. So I'm going to go through them, and then we're going to use these to prove some other true things about vector spaces as well, just like Euclid did with geometry. He started off with few and then got lots of theorems. And this is all stuff that's going a little bit afield of differential equations, but vector spaces, and this is all under the capstone of linear algebra, is probably the single area of mathematics that is maybe most important for all other areas. It just finds its way into just every other area of mathematics, and differential equations is just one of many. So it's good to see it for our use in differential equations, but it's good to just kind of be aware of it anyway. And it's kind of I don't know, it's just neat. It's just kind of like playing a game. So let's go ahead and get started. So any collection of things, okay, a set, which I'll call V, with two things you can do with these things in V. You can add them together, and you can multiply them by scalars. So that's scalar multiplication, and you can add them together. So it's vector addition, and then you can multiply them by scalars. And by a scalar, I mean just a real number. Sometimes people can use complex numbers or other scalars as well, but we'll always be using real numbers as our scalars, okay, as our numbers. So here's the 10 properties. The first one is, and by the way, I'm giving you some new notation here too that might be new to you. This symbol here is the symbol for all. It's just used so often in mathematics that instead of using that phrase all the time, we just use this symbol. Here's the other one that comes up a lot. It's called there is, or there exists. Those two come up so often that we just have a symbol, a little shorthand for each, okay? So this says, for all or given any two vectors in the set, two elements of the set, if you add them together, you're going to get something else in the set. And if you think about it, it's just got to be, if you're going to have any fun with this at all, it's got to be that way. It's kind of like playing tennis. If you're going to play tennis on the top of a skyscraper and there were no nets, so that every time you hit the ball went over the side, you wouldn't be playing tennis very long. And similarly, if you take these two vectors and add them together and you get something that's no longer in the set, well, then you're not going to be playing with your vectors very long. It's kind of like playing chess, where you can go off the board. If you can go off the board and whatever, you're not going to be playing chess very long. Okay, so given any two of them, add them together, you got to be back in there again. And similarly, the other thing we do is we multiply them by scalars. So given any vector, if you take any real number and multiply those two things together, again, you got to be another vector in the space, okay? And so, as I say, if it weren't that way, then we wouldn't be playing very long. Okay, what are the other ones? Next one says that if you take any two vectors and add them together, it doesn't matter which order you add them. If you take x and add it to y, you're going to get the same thing as if you take y and add it to x. That's called the commutative property, maybe something that you've heard before. Here's the associative property, another thing you might have heard. You take any three vectors, and if you first add x and y together and then add z to that, you're going to get exactly the same thing as if you first added y plus z and then added x to that. So you're going to end up with the same thing either way. And again, these are all things that are true of vectors as being these arrows, right? It doesn't matter whether if I have three arrows, three vectors like this, right? It doesn't matter whether I first add these two and then add this one, or whether I first add those two and then add this one. I'm going to end up at the same spot. Okay? Here's another one. It says there is, here's the symbol there is a particular vector, maybe I should say here something which is in V. Okay, it's in V. By the way, this symbol means is in, or is an element of. So there is a vector which we'll call theta, which is in V, such that, there's yet another phrase, such that, ST, such that what is true? Given any vector, if you add theta to x, you're just going to get x back again. So it doesn't change it at all. It's called the identity vector, okay? So that's got to be true. Number 6, once you have this identity, what else does it say? It says you give me any vector, there's going to be another vector with the property that if I add these two together, I'm going to get that identity vector. Okay, so again, if you think of these things as being vectors like this, here's the identity vector. It would be just that thing itself, that dot. If you add that to that, you're just back there again. If you take this one and add it to this one, you add those together, notice what you're going to do. You go head to tail, you're going to be right back where you began again. So there is an identity, or I should say it's called the inverse. There's one that undoes the original one. So you get the identity back again. Here's one that seems really strange. You give me any vector, and if I multiply that vector by 1, I'll just get that vector. It just doesn't seem, that seems so obvious that you wouldn't even have to say it. But the point is, it's got to be stated, otherwise you can't assume it's true. And it's similar to some of the things that Euclid did with geometry. Remember in geometry, one of the 5 axioms is all right angles are the same. It just seems so obvious. Well, of course all right angles are the same, but that's one of the 5 axioms. Without that, you can't get everything else from geometry. So that's kind of interesting. We'll see in a minute where that becomes important. Here's another one. It says that if I have a couple scalars, I can first multiply those scalars together and then multiply them by a vector, or I can take the vector and multiply it by one scalar, and then once I get that as a result, I can multiply that by the other scalar, and I'll end up at the same spot either way. Okay? That's got to be true. Again, these things seem reasonable because you're kind of used to them from just numbers, but these are the things that have to hold to be a vector space. Here's another one, distributive property. It says if I take a scalar and multiply it by the sum of 2 vectors, I'm going to get exactly the same thing as if I first add it to x and then multiply it by x and then multiply it by y and then add those 2 together. And then the last one is kind of the flip. I can take 2 scalars and add them together and multiply that by x, and I'll get exactly the same thing as if I first multiply x by a and then multiply it by b and add those together. So there they are. Those are the 10 properties, and in a linear algebra course you would take an hour to go through this stuff carefully. So I'm kind of reviewing it, and if you're interested, you can I've got it in my book, in my textbook, but you can find a whole textbook on linear algebra and dig into it in depth. But anyway, once you have those 10 rules, it's kind of like playing a game like Dungeons and Dragons or something like that, where you got, okay, these are the rules. And now that you have the rules, what are some other things that are also true? And so here's one thing which is also true. One thing which is true is that this identity is unique. In other words, there's only one identity. There aren't two different vectors which each have that same property. Okay? So this is what's kind of fun, is to prove these things. So I'm going to prove these first 5 just to kind of show you how it's done. It's just kind of neat. It trains you in careful thinking, because these are the only 10 things we can assume, and using those 10 things we got to prove this. Okay? So here's how we prove that the identity is unique. So I start with this. I say suppose theta 1 and theta 2 are identities. Okay? So if the identity is unique, then I have to show that theta 1 is equal to theta 2. Agreed? So here's what I do. Then I can say, then theta 1 is equal to, well, since theta 2 is an identity, I know that for anything, since this thing is an identity, I know that I can add that to anything, and I'm just going to get that thing back again, right? That's what it means for this to be an identity. I can add it to anything, and this is going to be, and this is, it's going to give me this thing back again. X plus the identity gives me this thing again. So this is equal to this. Now I can just flip these 2 around. Why can I do that? Because given any 2 vectors, I can write them in either order. And now what do I know? I know that since this thing is an identity, we're assuming that's an identity, what's true? If I add that to anything, I'm going to get that thing again. So this is an identity, so if I add it to in this case, theta 2, I'm going to get theta 2 again. So there we just proved it. So theta 1 is equal to theta 2, so it's got to be unique. Okay? So it's got to be unique. Okay? Let's show that the inverse is unique. Look at here. Here I just said I said there exists some y such that when I add these two together, I get the identity. So now, suppose, so here, that's the proof for the first one. Suppose that y1 and y2 are both inverses of x. Okay? Of x. So, what do I do? Well, I say, okay, y1 is equal to theta plus y1, or I'll say y1 plus theta. Agreed? Because theta can be added to anything and you just get that thing back again. And now I can write y1, and in place of theta, I can write whoops, there's a plus right there. I can write x plus y2. Agreed? Because the y2 is an inverse of x, and so y2 plus x is equal to theta. So this can be put in place of theta right there. So I've got that. Now I can reassociate them. See where all these things are needed? Now I can reassociate them and write this as y1 plus x plus y2. And now I can flip these, commute those. I'll just do it right underneath here and write x plus y1 plus y2. And now, since this is the inverse, or an inverse of x, this gives me theta. So that gives me theta plus y2. And now I can flip these two back again and get that's equal to y2 plus theta, and y2 plus theta is just equal to y2. See that? So there you go. There's a really careful proof for every single thing I did came from one of those steps, okay? And when I teach this as a course, I have the students actually put, like this one here, they would put, I'm using the commutative property, so I would put a little Roman numeral 3 above that. And here's the associative property, so I would put a Roman numeral 4 above that, and so on. So every single thing they do, they say why is it they can do it. So anyway, there we just showed that the inverse is unique, okay? And since the inverse, for lack of space, I'm going to have to get rid of this now. Since the inverse is unique, we call the inverse negative x. We just put a negative sign in front of the x, and that's the notation for the inverse of x. So in other words, x plus negative x is equal to theta. Okay? So those two are unique. How about this next one? This is an important one. Okay, we're saying that if x plus z is equal to y plus z, then we want to prove that basically you can get rid of the z's and say that x has got to be equal to y. That's what we want to prove. Okay? So again, these are things you do with numbers, they're things you do with arrows, they're things you're used to doing, but we have to prove that you can actually do it in general for any vector space. So how do we do that? Here's what you do. You start by, you say x. Let's see, how do I do this again? I can't remember. Oh, okay, here's what we do. We start by saying suppose x plus z is equal to y plus z. Okay, we're going to assume that this is true. and then we have to show that this is true. So we're going to assume that this is true. So I'm going to say then x is equal to x plus theta. Agreed? These are clever enough that I need to watch my notes as I do it, which is equal to x plus, now what do? Oh, z plus the inverse of z. Do you agree that z plus the inverse of z gives you theta? So that's true. Okay, and now you can reassociate and write that as x plus z plus a negative z. Okay, and now we're assuming that this is equal to this. So now I'm going to just go right underneath and say that that's equal to y plus z. And now I just go backwards again. Oops, I got to go plus my negative z. Now I reassociate again and go y plus z plus a negative z. And now this becomes y plus theta. And y plus theta is the same, is of course equal to y. So there you go. So I just think it's kind of cool. This calculus gives me goosebumps because of the powerful things you can do with it. This gives me goosebumps because I realize that you're building up a solid foundation, which we'll talk about as soon as we're done with this, for a lot of mathematics by carefully going through these proofs. So there we just proved it, that if this is equal to this, then sure enough, x is equal to y. So we've got that one. Okay? Going to do a couple more. Let's see, what's the next one? Going to prove, okay, going to show that 0 times any vector is equal to the identity vector. Okay, this is the real number 0, and if you take the real number 0 and you multiply that by any vector, you're going to get the identity. How do we do that one? Here's what we do. We start like this. Okay, here's the proof. We start by saying 0x is equal to, and again I need to remind myself how this works, 0 plus 0x. Do you agree that 0 plus 0 is equal to 0? Those are just real numbers, so that's true. Now, notice that we can use this property and say, oh, that's equal to 0x plus 0x. Okay? And now, that whole line implies that 0x plus theta is equal to 0x plus 0x. Agreed? Because I can add theta to anything and I haven't changed it. So this is equal to this. And now I can finally use this one and say, oh, well, this one says I get rid of what? I get rid of the second one. So let me turn them around. Let me turn this one around and write it as theta plus 0x is equal to 0x plus 0x. And now finally this says what? I can get rid of the second one. And so these two go away. And I end up with 0x is equal to theta, or theta is equal to 0x. There you go. Okay, so there's that one. Okay, one more to go. And this last one, again, it seems kind of obvious, but it's not. It's got to be proved. This says that if I take the scalar, the real number, -1, and I multiply that by x, that I'm going to get the inverse of x. Okay? These are saying two different things. This is saying I take the scalar, I take the vector x and I multiply it by the scalar -1. Let me make sure that you're still there. Okay, you are? This says I take the vector x and I multiply it by the scalar -1. That's what I do. This is saying this is the inverse of the vector x. The thing that when I add it to it, I get theta. I get the identity. So those are two different things. I want to show that those two different things are actually the same. So what do? Well, we do this. Okay, this is number 6. Yep. So I say, okay, x plus negative 1x, okay, here, this is going to be the proof. X plus negative 1x is equal to 1x plus negative 1x. Oh, that's where, how can I say that this is equal to this? See that? In order to make that step right there, I have to assume this as being true. That for any x, that if I multiply it by 1, I get that thing again. If that weren't one of my 10 conditions here, I wouldn't be able to do this step. But you see why that step is needed for this proof right there. And now I can use this property going backwards and say, oh, okay, I have a scalar in front of each of these. I can combine them. So that becomes what? 1 plus a negative 1 times x. And now these are just real numbers. Those just act like real numbers act. That's going to be 0 times x. And 0 times x we know is equal to theta. Okay? So there you see that when I add this thing here to x, I get theta. And now I also use the fact that, I guess I erased it, but that or did I? Oh, that the additive inverse is unique. There's only one of them. So I can say, since the additive inverse, or the inverse, I'll just say the inverse, since the inverse is unique, we already proved that there's only one of them. Since there's only one of them, and since this thing gives you theta when you add it to x, since it's unique, this thing right here has got to be equal to that inverse. So there you go. Okay? So very cool. So as I say, this is cool stuff, and this is now we've got not only the 10 things that we started with as assuming true, but now we've got these as well. And in the book, you'll see there's a couple more things that I'm not going to go through those proofs just for sake of time, but I also mention that negative a times x is equal to a times the inverse of x, and that's all equal to the negative, or I should say the inverse of a times x. Okay? This is saying that I first take the negative of a, that's just a real number, multiply that by x. That's equal to a times the inverse of x, and that's equal to the inverse of ax. Those things are all the same. And the last thing which is true is that if x plus y is equal to x, the only way that can happen is if y is the identity. So those are two more, not just for the sake of time, not going to go through those, but they're try them on your own, okay? See if you can do those on your own. So, okay, very good. So those are so natural. I'm going to just erase that for the sake of space. And now, let's see once why vector spaces are so important. They're important because there's so many things in mathematics which are, in fact, vector spaces. Not only arrows in the plane, but also, first of all, arrows in 3 space, or in 4 space, or in n space. You can have arrows like this in 3 space, and you can use quantities like x1, y1, z1 to stand for the coordinates of this point. And so if this is the x-axis right here, and this is the y-axis, and this is the z-axis, then if you start at 0 and go up to this point and think of that as just being the arrow, if you want to, you can just think of it as being the arrow, then that vector is named x1, y1, z1, where those are the coordinates of that point, okay? The x, y, and z coordinates. So that whole collection of things is a vector space. Let's see why. If I add two things like that together, let's take another one. Say here's another one right here. So this one right here is x2, y2, z2. And so how do you add them together? Well, let's call this vector. I'll call this I'll call this like this. x1, where x stands for the. Let me call it v1, just so it's not too confusing. I'll call that v1, and call this one v2. Then I don't even need that notation. Okay, hold on just a second. Okay. So let's see. How would we add them? We'd say that v1 plus v2 is what you get by just adding the coordinates together. So this would be the vector x1 plus x2, comma, y1 plus y2, comma, z1 plus z2. And so if we add them together that way, and if you multiply them by scalars this way, let me just take a times v1, and I'm just multiply it like this, a times x1, comma, a x2, not x2, but y1, comma, a z1. There's a way to multiply them by a scalar. And if you add them this way, and if you multiply them this way, then all 10 of these properties hold. And so that means that R3, we call this R3 for vectors in 3 space, is a vector space. It satisfies all these quantities. Now, I should be clear that this is the natural way to do it, but you could try something else. You could say this is just equal to this, where you multiply the first thing by a and you leave these alone. And this is kind of fun to play with, but if you try your own rules for addition and multiplication, most of the time, unless it's the kind of the natural one that you're maybe used to, it's not gonna satisfy these things. It's gonna mess up someplace or another. I can't think right now which one that one doesn't satisfy, but something or another, it more than likely misses one of them or another. Okay, so I'll leave that to you. Again, this is stuff that if you wanted to spend more time with vector spaces, you can play with this quite a bit. Okay, so there's a vector space. Okay, it turns out that like 2x3 matrices. Let's look at 2x3 matrices. Something of the form A, B, C, D, E, F. Okay, there's 2 rows, 3 columns. And here's another, let's call all these ones here, just to keep it simple. And here's another one, A, B, C, D, E, F, and call all those 2's. Okay, so there's a matrix, and if we add them together in the way that you would kind of think natural, A1 plus A2 dot dot dot, F1 plus F2 all the way through, and if you multiply them by a scalar and say, oh, this thing times, I've already got an A there, so let me make this alpha. Alpha times that is equal to alpha A1 dot 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 alpha F1, and just multiply everything through by alpha, then it turns out that this is another vector space. So many things in mathematics are vector spaces. Here's here's some important ones. If you just take let's make it just continuous functions. Continuous functions on the real line. Okay, all continuous functions on the real line. So they're all functions that, I tell you, my marker's starting to mark out. Let me grab another one here, see if this one's good. There you go. Okay, so a function like this. There's a continuous function. Here's another one. Okay, there's another continuous function. So we'll call this function f and call this function g. And they go through the whole real line. And we're going to add them together like this. F plus g of x is what you get just by taking f of x and adding it to g of x. So that's the way you typically add functions. You just take this value and add it to that value, and you get the sum. And if you multiply by a constant, all you're doing is taking the value of the function and just multiplying that by alpha. So if you multiply this by 3, it would be just 3 units up, and so on. So that's a way to add things and multiply them by constants, and it turns out that that's a vector space. Look at it. Just look. If you add two continuous functions together, you get another continuous function. That's why in most any calculus book, you'll see a little box where it says, if f plus g are continuous, then f plus g is continuous. And you'll also see that alpha times f is continuous. So the authors, even though they don't really tell you why, they're basically saying these things are kind of like vector spaces, because if you take any two of them and add them together, you're there, and if you multiply it by a constant, it's going to be there. So that's really what they have in mind. Let's see, what's the identity function here? Do we have a continuous function which is identity? Sure, right? If I add the 0 function to anything, I'll just get that function back. Okay? So now that I have the identity, does each function have an inverse? Sure. Can I draw it? I don't know. Not very good. But it's just the negative of this one, right? It's just the negative of f. And by adding those together, sure enough, you get this one. And again, you can see that it satisfies all of those properties. So that's the key thing. If you have differentiable functions that are differentiable, where the derivative always exists. If you add two of them together, you get another one. If you multiply them by a constant, you get another one. So all those collections of things are all vector spaces. Okay, they're all vector spaces. So again, if you want to try to find some things that aren't, try this, for example. This is a fun one I like to give my class. All matrices. All matrices. I defy you to show that the collection of all matrices is a vector space, okay? As big as you want, okay? Each one is some matrix, or even if you want to say all square matrices. However you want to do it, if you just say all of them, you're going to have trouble. I think it's impossible to show that that's a vector space. If you say all matrices of dimension m by n, now you're good, okay? Like we did with 2 by 3 matrices, okay? Then you're okay. But if you just say all of them, then you're going to run into trouble there someplace or another. Okay? So let's see. What else is in this section? Okay. Here's the final thing. Once you have a vector space, let's just let that represent a vector space V, then you can sometimes you can take a subset of that vector space, and the subset is just a collection of things that are in here, and sometimes that subset will itself be a vector space. Okay, so for example, let's just take let V be equal to, let me use the same notation I have in the book, R 2 by 2. So these are all 2 by 2 matrices, okay? So these are all things of the form A, B, C, D, okay? It's all 2 by 2 matrices, okay? Okay, then I'm going to say W, which is equal to everything of the form A, B, C, 0 is a subspace of V. It's a subspace of V. What do I mean by that? I mean that everything in here is also in there. Do you agree with that? That everything in here is also in there. So it's a subset. But also, it all by itself is a vector space. That is, it satisfies all 10 of these properties. Okay? Let's go through and see once why this satisfies all 10 properties. Well, first of all, I can add things in I can add two of these. Oh, this is important. I shouldn't go through this carefully. If I take two things in here, look what happens. A1, B1, C1, 0 plus A2, B2, C2, 0. Do you all agree? If I take two things and add them together, the way we add 2 by 2 matrices, what am I going to end up with? A1 plus B1, A1 plus A2, B1 plus B2, C1 plus C2, and then 0 plus 0, of course, is 0. Do you all agree? That's going to give me something else in W, and that's what's so important. If you take any two things in there and add them together, you got to be able to get something else in there. And sure enough, if I take two things in W and add them together, I get something else in W. So that's true. How about this one? If I take this thing and multiply it by alpha, let's just multiply it by alpha. What do I get? I'm going to get alpha A1, alpha B1, alpha C1, and of course alpha times 0 is 0. So sure enough, I get something else that's in there again. So it satisfies those two. What's the third thing? If I take them and add them in either order, I'll get the same thing. Well, we know that's true because we already knew that was true for everything in here. So in particular, it's true for things like this. It's true for all of these. So it's going to be true for this. So this one we get free. This one we had to check. This one we had to check. I'll put an F there for we get it for free. This one we get for free. Because again, if I take any three things that look like this, they also are in here. And we know that anything in here satisfies this. And so anything in here also has to satisfy this. So we get this one for free. Okay? What's the next one? The identity has to be in there. Well, that one we don't get for free because the identity for this is this right there. There's the identity. There's the thing that I can add to anything in V and still get something in V. So that's the identity. Does that happen to be in W? Sure. In order to be in W, what do I have to have? I just have to have a 0 right there, and sure enough, I do. So this one I had to check, but sure enough, it's there. Okay. What about inverses? Okay. I know that anything here, if I add this to it, I'll get the 0 vector, right? I'll get the 0 vector. Okay. Is that going to be true for something of this form as well? Sure. Let's check it out. Take this thing and add it to negative A1, negative B1, negative C1, and 0, and I'm going to get the 0 vector. Okay, so this one I had to check. This one I get for free because I know that this is true for everything here, so it's going to be true for everything in here. So that comes for free. All three of these things are true for everything here, so it's also going to be true for everything in here. So that's going to be for free. Okay? So the moral of the story is, if you have a vector space, and then you take a subset of it, and you want to know whether this subset is itself a subspace, that is this itself a vector space, these are the four things that have to be checked. Those four right there. And actually, it turns out that you don't even have to do that much. All you have to do is these two right here. Because if you show that x plus y in, let's call this W, implies that, I'm sorry, if you show that x and y in W implies that x plus y is in W, and if you show that if x is in W implies that any constant times x is going to be in W, then these two come for free. Why do they come for free? Because we proved in the theorem, which I erased, that what if these two things are true. First of all, we want to show that the identity is in there. But look, since this is true, what do I know? All I have to do is take x in W, and then I can multiply that by 0, and so 0x is in W. But what did we prove in our theorem? We proved that 0x is equal to theta. So that implies that theta is in W. See that? So again, we can, oops, let me make sure that you're still watching again. You keep going to sleep on me here. Okay, very good. And so there we've shown that theta is in W. And similarly, we know that if x is in W, then negative 1 times x is in W, because we're assuming that any constant times x is in there. And what's negative 1 times x? That's the inverse. And again, that comes from our theorem. So it's really nice. It just shows how once you prove these theorems for general vector spaces, you've shown them for everything that happens to be a vector space. You don't have to. Once you show that anything is a vector space, you know that it's going to be true for it, because you've shown it in general. Okay. Well, that's the nice thing about doing things in general. If you show it in general, then once you show that something is a vector space, you know it satisfies all of these rules. Okay? So that, with apologies, is a very fast introduction to vector spaces and subspaces. And so this is going to be important throughout the course with functions and differentiable functions and so on. So we will be using this as we go. So that is the end. Let me just make sure here. The end of section 5.1. Very good.